to determine our test dates. Just going to see if we can finish this last problem of 3.4. Well, arguably 2 more 3.4, but the last bit's really short. Knock out the couple of things we're doing in 3.5 and then 3.7. I don't know. I'm going to polynomial without any true normal factoring method. This is just, all right, we list a couple zeros that might work. We find at least one that does work via synthetic division, because we'll need to factor the polynomial using the zero that works as well as the quotient. And then from the quotient, if that's quadratic, we factor it or quadratic formula it. If it's not, like this problem coming up will be, that we haven't seen yet. And it's not just x to the fourth, I haven't finished writing. You might have to do the whole process again. So if you have not watched the previous videos, you're going to need to watch those. You might not quite understand this, maybe just catch it later, because I don't want to go over all of the steps again. So x to the fourth minus x squared, sorry, not x squared, 2x squared. It was lagging, so it threw me off, minus 16x minus 15. And our goal here, the instructions were to find all zeros of the function, not just the rational zeros. Remember, the rational zeros you can find with the synthetic division, but there are irrational zeros, or non-rational zeros for the ear part, non. Find at the end once you get it down to quadratic. We don't really have any good methods besides that. But we said that we promised that you would always be able to get some rational zeros out, and then if there are any things with square roots or i's, it always pops out at the end. So here's our function. So first thing we do is we list our possible rational zeros, which were plus or minus the factors of the constant divided by the factors of the leading coefficient, which is not a 0, it's a 1. So we're listing all the different factor pairs of 15, which are 1, 3, 5, and 15, over all the different factor pairs of the leading coefficient, which is a 1. Well, the only number that goes into 1 is 1, which clearly we don't need to write the divided by 1, so it's just plus or minus 1, 3, 5, and 15. And I will remind you this again, in terms of testing, any problem that I ask you to find the zeros of with this method, this leading coefficient will be a 1. Now I said that if the problem only asks to list the possible zeros, it doesn't ask you to check them and find all zeros. That leading coefficient can be anything, so this bottom number could have a whole series of numbers and commas as well. So just understand that I'm keeping one type of problem simpler because it will make it way, way, way simpler, and the other type, it doesn't really matter. All right, so this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 8. This is 8 PR. Let me not write these that way. So there are 8 possible rational zeros that, in theory, we may have to try all 8 of them in synthetic division if we keep just not finding any that work. But I said, I try to make it so that you can find one that works after the first, second, or at least third, or at most third, really, or fourth. But you can use a graphing calculator to kind of push you in the right direction, but you still have to show your work. You still have to show the synthetic division. To get the quotient, your calculator is not going to give you all that stuff. And your calculator, if there are irrational zeros, it won't show them to you. So I'm going to pretend like I don't have my calculator today, and I'm just going to go start trying these. So 1, I'm going to try positive 1 of the possible rational zeros. Now I'm going to do this wrong for a second. I got 1, negative 2, negative 16, negative 15. This is wrong. Why is this wrong? Because here's our x to the third term. There is no x cubed term written, but that is a very important piece to have there. It's a placeholder. So this is like we've missed the x cubed column. 0 in its place. So we'll do the 1 for the x to the fourth, a 0 for the x cubed, the negative 2 for the x squared, negative 16 for the x, and the negative 15 for the constant. So many students miss this, and then everything is wrong because of that. All right, the process goes, bring the first number down, multiply, add, multiply, add, multiply, add. 1 times 1 is 1. At this point, if you're still not following along with me, that means you're not paying attention to the lectures, you're not replicating it in your homework, you're not taking good notes, is usually what happens, because we've done this like 30 times by now, maybe even closer to 40. All right, 0 plus 1 is 1. 1 times 1 is 1. Negative 2 plus 1 is negative 1. Negative 1 times 1 is negative 1. Negative 16 plus negative 1 is negative 17. Negative 17 times 1 is negative 17. Add those and you get negative 32, which is not 0. Remember, our goal is for this to be 0. So positive 1 is out. It is not a 0. It will not work now. It will not work later, so we don't have to try it again. Let me just kind of separate this like that. So let's try negative 1. And then same numbers to the right, 1, 0, negative 2, negative 16, negative 15. Some space, plus sign. Bring the 1 down. 1 times negative 1 is negative 1. 0 plus negative 1 is also negative 1. Negative 1 times negative 1 is positive 1. And man, if you're in this whole process, you've practically ruined the problem. You've got to be careful. I'm not going to act like I never make a mistake, but if I make a mistake, I have to check my work and I catch it 99.9% of the time, 0.8% of the time. Negative 2 plus 1 is negative 1. Multiply, you get positive 1. Negative, negative, positive. Negative 16 plus 1 is negative 15. Negative 15 times negative 1 is positive 15. And look at that, they add to 0, which is exactly what we want. That means that negative 1 is a 0. And it also means that x plus 1 is a factor. From right to left, not using red for wrong, that's the remainder, the constant, the coefficient of x, x squared, and x cubed. Another thing, back when I was doing this wrong, when I didn't have that 0, what you would have ended up seeing is you wouldn't have had this x cubed bit, you would have only had an x squared, and you might remember that I said, all right, if this is x to the 4th, the next thing should be an x to the 3rd. If it's an x to the 3rd, the next thing should be an x squared. So it's always supposed to go down by 1 degree each time. So if you go from a 4 to a 2, that is an instant red flag. All right, so f of x, I said switch it to blue, you silly program. Will now be, instead of writing what we have in black ink, it's the factor we just found, x plus 1. If negative 1 is the 0, x plus 1 is the factor. X plus 1 is the thing we divided by here. Then open a parentheses and write your quotient, which is 1x cubed minus 1x squared minus 1x. I don't need to write those ones though, and then minus 15. Now this is the first time this has happened by our examples. I'm going to scroll back to the previous 3 examples and just kind of compare and contrast. So example A, B, and C, these all started with a degree of 3. Quotient ended up having a degree of 2, which means we could either factor it, as we did here, or if it wasn't factorable, like in B and C, we ended up doing the quadratic formula, or if you preferred completing the square. However, okay, so those problems we went from x cubed to x squared. Just undoing all my highlighting. Put that there permanently. Fourth, to factor it sometimes. Sometimes this is a 4-term polynomial that's factorable by grouping, but spoiler alert, this one is not even close. So we have to repeat the whole process. This thing, this negative 15, and this 1, and we list its possible rational zeros, which are still the exact same. So it's the exact same PRZs, but we skip positive 1. We're going to skip 1 because it failed here, which means it'll fail here. However, we can't skip one that worked because it could have a multiplicity of 2 or 3 or 4, which means it could be a factor of this one. And then when you get the next quotient, it could be a factor of that one. You could have the same 0 occur 5, 6, 17 times if your polynomial has a degree of 5, 6, or 17. So we're going to try the -1 again, but now again we're using the quotient here, so the coefficients that go to the right are 1, -1, -1, and -15. So 1, -1, -1. I'm spacing this out way more than I need to. Here we go. And then same synthetic division process. Shouldn't be any surprises here. So bring down the 1. Multiply times the -1, which is -1. Add, you get -2. Multiply, you get +2. Add, you get +1. Multiply, you get -1. Add, and you get -16, which is not 0, so that doesn't work. So -1 only worked once, which means its multiplicity is 1. So now -1 is in the trash can for the rest of the problem. So now let's go up to, let's see, our possible rational zeros were plus or minus 1, which we've already taken care of those as possibilities, plus or minus 3. And I said to go in an ascending absolute order, so let's try the 3 out. I can't guarantee that this is the best order in the real world outside of this course. But for us, it's generally the best way to approach it. And again, if you don't want to just work blindly, you could go, oh, well, let me pull out my calculator, let me graph the quotient, and that'll very easily point me to the one that, at least one that works. All right, bring down 1. Okay, he's going the other way. I'm going to have to mute in a little bit because the trash truck's coming around. 1 times 3 is 3. -1 plus 3 is 2. 2 times 3 is 6. -1 plus 6 is 5. 5 times 3 is 15. And look at that, 0. So x equals 3 is a 0. And that means x minus 3 is a factor. All right, so now what we're going to do is we're going to take this function and we're going to rewrite it. We'll leave the x plus 1 alone. We're not changing that. But we are going to change this. We are going to factor that using what we just found, that x minus 3 is a factor, and then we'll do the quotient after it. All right, so what is the quotient? Echoes remainder, which doesn't matter, constant, coefficient of x, and x squared. And some people really like to write what the quotient is to the side. I didn't do it for that one, but I'll do it this time. That would be 1x squared plus 2x plus 5. So our function is now even more factored into the x plus 1, which we leave alone, the x minus 3, which we just found because positive 3 was the 0, times the quotient, which is, I'm not going to write the 1, x squared plus 2x plus 5. I was about to write 15. Undo, please. We already know everything from these 2 bits. All we're worried about now is this. Now that is quadratic, so while technically, yes, you can continue this possible rational zero process. Spoiler alerts, you're just going to waste your time because this, if you try to factor it, factors of 5 that add to 2 don't exist. It's prime. So that means we need to use the quadratic formula for setting the x squared plus 2x plus 5 equal to 0. Remember, the whole thing is we're setting this function equal to 0. It's just I never write the equals 0 before because all of the work implies it. So our a is 1, our b is 2, and our c is 5. So x equals -b, so -2, plus or minus, big square root. B squared, which is 2 squared, minus 4 times a, which is 1, times c, which is 5, all over 2a, which is 2 times 1. And then it's just arithmetic. All right, so -2 plus or minus the square root of 2 squared is 4 minus 4 times 1 is 4 times 5 is 20. All over, I didn't need my square root that big. Here we go. I'm going on mute for a second. And ironically, that might be the quietest that truck has been all semester. All right, so again, 4 minus 20 all over 2. 4 minus 20 is negative 16, so that's negative 2 plus or minus the square root of negative 16 over 2. But we know the square root is negative 16. It's 4i, not just 4, 4i. And 2 is a factor of all the tops and bottoms. There's no square root, so we can reduce this. So we can take 2 into all of these. 2 would go into negative 2, negative 1 times. 2 would go into 4, 2 times. And then a 2 in the bottom 1 time. But I don't like leaving that there. You can leave it in your notes. I just don't like leaving it in mine. So that becomes negative 1 plus or minus 2i. We don't need a 1 in the bottom. We don't need to write over 1. So that would be the last two zeros. So separately, I'll scroll back in a second. We had this one, and then these two zeros. So altogether, x equals negative 1, positive 3, negative 1, and if you have to separate in MyMathLab, negative 1 plus 2i, comma negative 1 minus 2i. By hand, I can just go negative 1 plus or minus 2i, though. So that is 4 zeros. It was a 4th degree polynomial, so that's a good sign. We might only find 3 zeros because one of them has a multiplicity. That's why we have to check a zero that previously worked in the quotient. All right, maybe you just don't trust this. Graphing calculator. Type in that function up here. X to the 4th minus 2x squared. Yes. Minus 16x is 15. I might have done a weird zoom last time, so let's fix that. And I can very clearly see there's 2 zeros here and here. If you try and trace it, you'll probably deduce that they're a nice whole number eventually. And it moves really quickly, so you only see the cursor on the screen for a little bit. But that looks like it's around the 3rd hash mark. If I type 3 and hit enter, y equals 0. 3 works. 3 works. And that would have confirmed. I could have done my synthetic division with 3 first. Or maybe you think, oh, that looks like negative 1. Let me type negative 1. And sure enough. So maybe you skip doing synthetic division on positive 1 because you can see it doesn't cross here. But negative 1 you would definitely need to do because it spits out a 0, which is ideal. So the point being, we could have started the synthetic division process on this problem with positive 3. We would have gotten a remainder of 0. We would have gotten a different quotient. But in the end, as we continue along this path and then do the negative 1 second, we would pop out the exact same zeros. The order you find them doesn't matter. It's just that you collect them all by the end. But I can definitely see that 5 and negative 5 don't work. 15 and negative 15 aren't on the screen, so if you wanted to know, you can change your window and change that to like a negative 20, a positive 20. This is just how far left and right it goes. That's what x min and x max mean. And we can see that negative 15 and positive 15 are not crossing points. But this picture does not tell us anything about the negative 1 plus or minus 2i. And guess what happens on a test? If I see negative 1 and positive 3, I'm going to know that either A, you try to use a calculator to cheat your way through the problem, and then I'm going to take all your points, or B, I'll look at your work and see all you did was the synthetic division and you didn't even try the quadratic bit. You just went through, you tried out the 5 and negative 5, the 15 and negative 15. You found that they didn't. Essentially everything I'm going to test on for maybe is let's say A, B, and C, your function you can basically write as some leading coefficient, some number that you would have to determine times x minus A times x minus B times x minus C. That's the factored form. If you know the zeros, you can write a factored form. If you know the zeros, you can write a factored form. That's exactly what we've been doing so far. But if I tell you all the zeros up front, you can go straight to the factored form of the answer. If you really wanted to expand it, you could. But most of the time, we don't like doing that. But the point of this is, I've never taught you how to factor something using imaginary numbers. I will never teach you how to factor something directly using imaginary numbers. But I can teach you how to factor if you know the zeros. And you can find the zeros based on that whole technique we've just learned. So once again, this is an amazing factoring ability, because all you got to do is just find all the zeros, and even if they're square roots of 5 or negative 17 over 3,000,042, just these wackadoo numbers that you would have never been able to take any normal factoring method to figure out, you can factor them. So if I told you the zeros are -3, +5, and then square root of 17, that says your function is some number, again, that you can determine by plugging in a point that they might give you. I'm not going to do any of this, it's just giving you the idea. And then it would be x minus -3, which ends up being an x plus 3, times x minus 5, times x minus the square root of 17. We have just learned how to factor something with radical numbers, which we have never done in our entire lives before. So what this also tells us, let's go back to something we talked about before, x squared plus 5 equals 0. If you wanted to solve this, you say, well, there's no perfect square here. I'm sorry, I want to do a minus, actually. I don't necessarily want that to be an I. Doesn't matter. So x squared minus 5, there is no difference of squares if this isn't a squared number, like 4 or 9 or 16. So you would have moved it to the other side to get x squared equals 5. Then you do your plus or minus square root, which people will still forget the plus or minus, and it's still going to haunt them. And that gives us x equals plus or minus square root of 5. So what that tells us is the factored form, even though there's no formula for this, there's no direct factoring method for this, it would be x plus the square root of 5 times x minus the square root of 5. The negative square root of 5 leads to the plus, the positive leads to the negative, because the zeros always change signs of the factored form. Or if you add x squared plus 4 equals 0, when you do that work, you eventually get down to x equals plus or minus 2i, which says the factored form, f for factored, would be x minus 2i times x plus 2i. It is an insane ability to be able to factor things with square roots and imaginary numbers where there's no true factoring technique for it. It's kind of like a Jeopardy problem. You find the answer and then you get the question, or you have the answer and then you get the question. The answer being the zeros, the question being the factored form. Usually we go factored form, then zeros. Now we're going zeros, then factored form. All right. So going back to the actual typed up part in these two examples, which I have had the answers spoiled the entire time and didn't even catch that. Good grief. And yes, I did that because Thanksgiving is around the corner. Disney can't lock up Charlie Brown forever. So if 2 plus 3i is 0, what must another 0 be? So for some reason, somebody tells you 2 plus 3i is 0. It automatically has a brother or a sister. I'm just not telling it to you. Well, that's because they always come in conjugate pairs, so that means that 2 minus 3i has to be a 0. You only change the sign of the imaginary term. So for this other one that only has an imaginary term, -7i, you could pretend that's like 0 minus 7i. So the conjugate would be 0 plus 7i, aka just 7i. And that is 3.4. Now, in the interest of time for section 3.5, because I'm trying to get 3.5 and 3.7 done, I need to get 3.5 done today. It looks like I'm going to have to push that test date back. I didn't want to, but we're probably going to have to. All right, so that's 3.4. That's the end of polynomial zero finding and graphing. I thought I erased that. I'm just going to erase the whole thing. Look away. Don't look at this screen yet. Look away. Hide your eyes. All right. This is what I want to start out with. Graphing rational functions. Remember, the word rational means fraction, but we generally use the word rational when we're associating x's in the bottom. So like x over 3 is technically a fraction, but nobody's going to call that a rational function because the x is only on the top. 3 over x, we would call that a rational function because the x is on the bottom. Now, we're not worried about when x's are just in the top because that's not what causes the problem. It's x's being in the bottom that causes the problem, because you can't divide by 0. I'm not getting into this table of values yet. This is a ways away. I'm focusing up here for now. So just ignore that for now. As a reminder, this is something we did back in chapter 2. The domain of a rational function is found by setting its denominator not equal to 0 and solving that. Because we're not allowed to divide by 0. It makes the world explode or implode on itself unless we're a supercomputer that can handle quantum computing and blah, blah, blah. We're not getting into all that jazz. So we're going to study these two rational functions to kind of get an idea of how they should look, and then talk about some of the features in these graphs and learn how to predict them without doing all the work I'm about to do. And we're going to focus on 1 over x first, and then 1 over x squared we'll just give you really quickly. So 1 over x has a name. It's known as the reciprocal function. Reciprocal meaning it just flips something. So 1 over x just flips the input. X would be the input, 1 over x would be flipping the input. So in other words, if you plug 2/3 into this function, the answer would be 3/2, because 1 divided by anything just means to flip it as a fraction. So if you plug in 5, the answer would be 1/5. If you plug in 10, the answer would be 1/10. If you plug in 52, the answer would be 1 over 52. But I'm not just going to plug in whole numbers to this. So you can kind of see the numbers here on the left. I am going to get to the graphing aspect now, so let's undo the scribbling. You're going to notice that I didn't just do like a traditional -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5 graph. I've picked my numbers very explicitly. I've gone from -100 to +100 in what I'd like to call multiples and divisions of 10. So I'm just going in factors of 10. So 2 zeros, 1 0, no zeros, now divided by 10, divided by 100. And I could keep going, divided by 1,000. I could do -1,000, -10,000, but this is going to get the point across. Then I could go -1 over 100, -1 over 1,000, -1 over 10,000, but I'm just stopping at -1 over 100. Then I go to 0, and I have an asterisk next to that for a reason. Then we go to 1 over 100. I'm just going to do the positive values of what I have above. 1/10, 110, 100. I could keep going, 1,000, 10,000, et cetera, et cetera. Now, these answers are just going to be flipping that number. So -100, when you plug it in, if you need to see the work, I'll do it at least for the first one. Good grief. I wonder if y'all heard that. I said that trash truck was quiet earlier. He wasn't just now. And brakes are screeching, baby. All right, f of x, I did not mean to write the x. F of negative 100 would be 1 over negative 100, which we don't like negatives left in the bottom. So let's put it in the top. And I'm going to erase this work because that's where my graph's going to go, as you already saw. And it's negative 1 over 100. I'm going to write this in a slash manner so that I have space. So plugging in negative 100, the answer is negative 1 over 100. Again, just the reciprocal of the original value. So if you plug in negative 10, if you flip it, you get negative 1/10. If you plug in negative 1, you get negative 1 over 1. But negative 1 over 1 is really just negative 1. So I'm not going to write that as a fraction, just a whole number. I'll show the work again real quick, but then I'll erase it. I'll show plugging in this one, f of negative 1/10. Now, if you understand the idea that it's a reciprocal, you know the answer is going to be negative 10, but let's show you why. So that's 1 over negative 1 over 10. That's dividing by a fraction, which means multiply by the reciprocal. So 1 times negative 10 over 1. And 1 times anything is the anything, so that's negative 10. See, if you take negative 1 over 10 and flip it, you get negative 10. I'm not lying. Leave the work up there for a second. But the eraser's coming in hot. Dividing by a fraction means multiply that by reciprocal. If you're going on to Math 162, which is pre-calc 2, trigonometry next, this isn't going away. If you're going to calculus, this isn't going away. Fractions are never going away. All right. So if we plug in negative 1 over 100, you're going to flip it and get negative 100. So this is kind of the weirdness of this function. When you plug in really, really big numbers, your answer is a really, really small number. When you plug in really, 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 really small numbers, your answer is a really big number. So if I plugged in negative 1 over a million, the answer would be a million. If I plugged in negative 1 over a billion, the answer would be 1 billion. There is an inverse relationship with these. There is a reciprocal relationship with these. What happens if you plug in 0, though? Well, that's literally sitting right there. It's undefined because you can't divide by 0. And that's why I had an asterisk next to that one. Now, plugging in the next 5 values is just going to be the exact same process as above, just no negatives. Flip 1 over 100, you get 100. Flip 1 over 10, you get 10. Flip 1, you get 1. Flip 10, you get 1/10. Flip 1 over 100. I'm sorry, flip 100 and you get 1 over 100. All right, I really wish I had a really good graph, and I kind of wish I hadn't erased it, but I'm going to do my best. The challenge of this graph is the fact that I'm not going 1, 2, 3, 4, 5. I'm going in those 1, 10, 100, so the spacing is critical. So I might take a little longer to make this. Oh, I can even, I left that there. So that's where the graph was originally. All right, so there's my y-axis. I'll do this as evenly as I can. Our x-axis. So the numbers on the y-axis we need to label are the blue ones, the negative 1 over 1, I'm sorry, the negative 100. That one is right here. Then we'll need the negative 10, excuse me, which if that's 100, this is 90, 80, 70, 60, 50. It's going to be like here. And even that is probably further out than it should be. Then I need to label negative 1, which is almost impossible for me to do. It's right there. Then I need to label the positive 1, which again is practically squeezing that axis. Then the negative 10, I'm sorry, positive 10, of course. Positive 10, and then positive 100 will be up here. And the x-axis, you'll have the same numbers being labeled. It's the same numbers labeled, just they're not paired 100 with 100, 10 with 10. So let's go all the way over here for negative 100, which would make this right here probably about the negative 10. It's getting really squished, but that would be the negative 1. I really can't write this, but right there would be the 1. About here would be the positive 10, and about here would be the positive 100. So negative 100 comma negative 1/100th. Now I can't even label that on these. Negative 1 over 100, this is practically 0. It is practically sitting on the axis. So I'm going to put a dot right here, and I'm trying to emphasize that it's above the axis. But I mean, it just barely. Just barely. I mean, you need to get out your ruler and go into the millimeters to get that really super accurate. So that's the top point. That was this one. I'm just going to work my way down. So negative 10 comma negative 1/10, so go left 10. Also, I messed up. This is a negative, and I did above. I should have gone below. It's really not even going to be seen, but hardly, but it's negative. It's supposed to be below. I was about to make a very critical mistake. So there's my negative 1/100. Negative 100 means left 100, then negative 1/100, so down 0.01, just barely down at all. All right, reset. Negative 10, so left 10, then negative 1/10. So now I'm going down, but not very much more. Then negative 1, negative 1, so that's left 1, down 1, so something like here. Negative 1/10 means I'm going to barely go left at all, and then down 10, which means it's really hugging the y-axis. That was this one, so I've done the first 4. Now the negative 1 over 100, which means I am really not going left at all, but I'm going to do it just for emphasis, and then down 100. So again, it looks like it's on the y-axis. Please understand that it's not on the y-axis. It is a millimeter from the y-axis. Then we can't even do this point right here because it's undefined. We can't graph undefined. We can't graph imaginaries or undefined. Let me show you what this left side looks like before I continue. No wiggles. This is just my bad artistic ability. And this is zoomed out pretty far, so I'll have to talk about this afterwards. But it's kind of got this shape going on. Oh, that was not that great. It's got this shape going on. That's still not that great. Come on, Rodney. It's got this shape going on where it's flattening out as you go left, and it's basically going completely vertical as you get close to x equals 0 because of that undefined aspect. That's what causes that. Now this, we're looking from negative 100 to 100, so it looks a lot more rigid, but when we're doing our problems, it's usually going to look a little smoother like that. Okay, now the right side of the graph, basically the same thing, but it's going to end up being up here instead. So positive 1 over 100 means barely go right, and then up 100. So hugging that y-axis. Then 1/10 comma 10 means go right barely, but a little more than previously, and then go up 10, so about here. Then 1 comma 1 means go right 1 and up 1, so about there. Then 10 comma 1/10, and 100 comma 1/100th. So again, the same kind of shape. It's just going practically straight up as you get close to that y-axis. And then it kind of takes a sharp turn and then pretty much just parallels the x-axis afterwards. But the important part is, ooh, that got ugly. Even though it might look like I'm crossing the y-axis at some point, I've never crossed either the y or the x-axis for this graph. And then arrows on the ends. So this is the picture. But again, we're not really going to be looking this far out usually. That was just for the emphasis of the flipping of the fractions and such. This is how we will picture them most of the time. This is a much more basic approach, like we were going from negative 10 to 10, and even this section is a little steeper than it might need to be. So for the graph of 1 over x, here's a much more basic picture of it. Let me zoom out so you can see everything. Because when we do graphs, this is not how we do graphs in pre-calc, is it? We learn a better method. We learn to know what the shape is, and then just take 1 or 2 or 3 key features to build that shape, not just blatant plug in this point, this point, this point, this point. We like intercepts because we like plugging in zeros, and then we liked finding other features for polynomials, but this has different types of features that we'll talk about. They're called asymptotes. So again, you will never graph a rational function this way again. What you do is you find out where these little dotted lines I've drawn up go, and then you just make the shape around that with 1 or 2 points instead of doing 10 or 12 points. So the blue is the actual graph itself. These red dotted lines are what we call asymptotes. Asymptotes are basically, imagine you're playing with your brother or sister, you're playing the I'm not touching you game. So you're getting as close as possible to taking your finger to touching the tip of their nose or their ear or their cheek or their arm or whatever it is, just to bug them. We're not trying to bug anybody here, but I'm just trying to use a fun example. You're getting as close as possible, but you can't actually touch them because then you're not playing the I'm not touching you game when you're like 4, 5, 6 years old, whatever. Or imagine that you're standing in front of a wall, maybe 10 feet away, and every time you want to move, you're going to move halfway to the wall. So first you're 10 feet away, and then you move halfway to the wall, which means you'll now be 5 feet away. Then you do it again, you'll be 2.5 feet away. You do it again, you'll be 1.25 feet away. Do it again, and you're going to be less than a foot away. And then do it again, you'll be less than half a foot away. So let's go there. Then you'll be 1/4 of a foot away, then 1/8 of a foot away, then 1/16 of a foot away, then 1/32 of a foot away. You're going to start moving in millimeters and then femtometers and nanometers, but your nose will never actually touch the wall. Because if you just move in half distances each time, you're never actually going to get there. Now, of course, it's going to get to the point where you're so close that it's going to be unavoidable touching it, but we're not a mathematical model. We're people. We have imperfections. So these don't have imperfections. They never, ever, ever touch. This horizontal asymptote says that this thing is approaching 0, but it never actually turns into it. Think if you plugged in the number 1 trillion, the answer to the function would be 1/1,000,000,000th. That's still not 0. You're going to have a really hard time physically deciphering the difference of 1/1,000,000,000th versus 0, but it's still not on that axis. And then counterpositively, when you get closer, when you start plugging in numbers really close to 0, when you flip them, they start getting extravagantly large. All right, so for the graph of 1/x, this is what it looks like. If you had 2/x, it would pretty much look the same. If you had something like 3/x minus 7, it would basically look the same, except these asymptotes may not be on the x and y axis, and that's the point we're going to be driving. I will show you the graph of 1/x squared as well, without doing all the table of values, but let me just tell you why it looks this way. When you have an x squared, when you go to plug in numbers like this, what happens to the negatives? That's right, they become positives. So everything that would have been below the graph originally, because those were negative outputs, now they're positive outputs, so it's now above the graph. See, the right side essentially looks the same. It is a little tighter in this corner, and I did not demonstrate that too well, but I'm not going to worry about this type of graph too much. It's just an introduction to it. So again, it's just the left side being on the bottom is now on the top because of the x squared. But please note, you will never graph one of these things and have it look like this. You will never have a rational function look like this, because why? It would fail the vertical line test. That's not a function. So please don't think that can ever happen. If it's a function, it can never happen. Now again, these little curves and everything, those dotted lines could be like over here, and then maybe it looks like this. They can also have a third section. They can actually look like you can have more than one vertical asymptote, and they might look something like this, where the outside still have that common shape, but then the inside might look like a quadratic or a cubic. Now I say look like because they aren't actually due to the asymptotes, they're stuck in there, but these are just possible other shapes of these. But these dotted lines are the main driving force of us being able to graph it, because we memorize this kind of curvature of the shape. It's kind of like a C, but as you get further and further out, either going up a lot or right a lot or left a lot or down a lot, you start hugging that asymptote. See, when I'm graphing one of these, first thing I would do is graph all my asymptotes, maybe find a point or two, and those 2 points, that's all you need. Because this point is surrounded by those asymptotes, it has to look like this, just based on memorization of shape and patterns. With that dot in that section, it would have to look like that. And I drew it in a poor spot, but you get the idea. Now here's the thing, we're a little short on time. I'm not going to be showing you how to graph these unless we can finish chapter 4 and still have a class left, and then we'll come back and do it. But I will introduce you to the asymptotes, how to find the vertical and the horizontal asymptotes, how to find those dotted lines, because past that, it's really just a little more work heavy, but it's not introducing anything convoluted. All right, so these asymptotes, what are they? How do we find them? How do we use them? Asymptotes are when one of these A or B in these arrow notations is an infinity and the other is not. So this is just a reintroduction of arrow notation. So as x moves to, say, negative infinity, the function moves to 0, or as x moves to positive infinity, the function moves to 3, or as x moves to negative infinity, the function moves to 4. That's what we're talking about here. So when we talk about vertical asymptotes, it would look something like this. So for the function that we just graphed, we just spent a lot of time on 1 over x. As you approach 0 from either the left or the right side, so that was when we went from 1 to 1/10 to 1/100th, or from -1 to -1/10 to -1/100th. As your x value gets closer and closer to 0, the function is either going to move to plus or minus infinity. That is this right here, this region right here. As your x value gets closer and closer to 0, we're either going down forever or we're going up forever. And it's different from side to side. Sometimes it's pointing in the same direction, sometimes they're pointing in opposite directions, and that's why we would need a point or two to establish that. So again, what I have highlighted here is what I just showed up there. As you move closer and closer to the origin, as your x gets closer to 0, this function in particular goes either up or down forever. Conversely, as you move left or right forever, that's with x moving to plus or minus infinity, your function moves to a height of 0. And that's what we see right here and here. As we go left or right forever, this thing flattens out, flattens out. So as x moves left or right forever, the function goes to 0. This whole idea is very similar to finding the domain. Look at this, as x goes to 0, it goes to plus or minus infinity. That's it showing that undefined aspect, which if you set the denominator not equal to 0, you would very quickly see that x is not allowed to be 0. So finding the vertical asymptote is very similar to the domain, with one exception. You have to reduce everything first if you can. If you can't, it's fine. But if something is reducible, there is a distinction of domain versus vertical asymptotes. So there's subtleties that we will get into. All right, so actually finding the vertical asymptotes. VA's vertical asymptotes can be found by first reducing a rational function and finding values that make the denominator 0. We represent vertical asymptotes by drawing dotted lines, dotted vertical lines. And a vertical line is always the form x equals a number. So if when you set your bottom not equal to 0 or equal to 0, whichever you're choosing, let's say you get 3. 3 is not the vertical asymptote. X equals 3 is the vertical asymptote. Without the x equals part, it's completely wrong and not even partial credit in a lot of teachers' eyes. I might give you a point, but I'm not giving you a lot of partial credit for that. You've got to remember that vertical lines are x equals a number and horizontal lines or y equals a number. Now I said, when we found the domain, we didn't reduce first, but for vertical asymptotes, we have to reduce first. That's a big distinction. So there's a slight difference in domain versus vertical asymptotes. So let's say that you factor the top and bottom and something does cancel. That's this. Any common factor top and bottom that reduced leads to a hole in the graph instead of an asymptote. So there's a distinction. And you can see the images of what an asymptote looks like, how that shoots this thing off to an infinity or negative infinity versus a hole. A hole does not shoot up forever or down forever. It just keeps following along the pattern. You've just got the tiniest hop in the world over something, and then you just keep going on. So functions that have holes don't always have these wacky features. Where does a hole come from? It's if you factor and something actually cancels. The thing that canceled would have a hole. Now, you can have asymptotes and a hole in a function. You can have multiple holes in a function. It's not something we usually see, but it could happen in the real world. You're not going to see a lot of problems in this course that have holes. I will do one example with it. And remember, you've got your graphing calculator that you can pull out to confirm this stuff. You just can't let it do all the work for you, because if I see an answer and I go back and I look for your work and I don't see work, I can take all those points back from you. So vertical asymptotes are found by factoring, reducing, and then setting the bottom equal to 0. Anything that factored and reduced out, you call that a hole instead. All right, now I don't want to actually leave all the work here. If I hit enter, does that bump? Yes, it does. Perfect. All right, so example 1, find all vertical asymptotes. For A, we're going to have f of x equals x over x squared minus 16. This is pretty easy to do. Again, the actual graphing aspect of it, I'm not going to throw on this test. I am hoping we have enough time to finish chapter 4 and come back to it, but that's kind of a day and a half segment on its own, and it's something that doesn't come back up in chapter 4, whereas asymptotes do come up in chapter 4. So I'm just kind of hitting the bare minimum. All right, so f of x equals x over x squared minus 16. Well, to find the vertical asymptotes, we have to reduce, if possible. Reducing, can't just reduce in this form, so you got to factor it. X squared minus 16 is x plus 4 times x minus 4. Well, guess what? Nothing cancels here. No, you cannot cancel any of these x's. You could only cancel something if this top was an x plus 4 or an x minus 4. So the vertical asymptotes, we do not care what the top is. If nothing reduces, we don't care what the top is at this point for finding VAs. We just take the bottom and we set it equal to 0. This is exactly the same as finding the domain because nothing canceled. If something had canceled, the domain would be different than the vertical asymptotes. And again, we'll see that example. Well, that's factored. Go ahead and set each factor equal to 0. So x plus 4 equals 0, x minus 4 equals 0. Subtract 4, add 4. You get x equals negative 4, and x equals positive 4. That's it. That's the whole problem. Our vertical asymptotes are negative 4 and positive 4. If I asked you to graph this over here at negative 4 and positive 4, you would just be drawing vertical dotted lines there. And then we'd have many more things to do after that. So those would be lines that our function can't cross. All right, B. And this one, the vertical asymptotes mirror the domain. The domain would be everything except negative 4 and positive 4. Let's change up this polynomial, I'm sorry, rational. I don't know why I said polynomial. Excuse my misspeaking there. Let's change the top to have an x plus 4 instead of just being x. Oh, wow, big crazy difference. It's got to be the exact same problem, right? Well, Let's find out. All right, so we said we cannot just take this and do all this stuff. You can't do that. If the problem is factorable and reducible, you must do that first. And guess what? It's still factorable, the exact same factor as last time. But check this out. You have common factors top and bottom now. X plus 4, they cancel. If the top goes away, you need a 1 in its place, giving us just 1 over x minus 4. So our vertical asymptotes are not setting x plus 4 and x minus 4 equal to 0. It is only setting the x minus 4 equal to 0. Now you might be saying, well, Mr. Beckner, I don't believe you. Don't worry, we'll graph these two functions after this, and hopefully you'll believe me a little more, at least by example. Add 4 to both sides and you get x equals positive 4. So the last problem, which had 2 factors in the bottom, had 2 vertical asymptotes. But the second problem, which had 2 factors in the bottom, due to a cancellation, only has 1 vertical asymptote. Now, I did only ask for the vertical asymptotes, but I want to put this extra memo here as well because it is important. We said that any common factor top and bottom that leads to a hole, any common factor top and bottom leads to a hole in the graph. So I just want to point out that since x plus 4 canceled, that means there is a hole at x equals negative 4. Remember, factors and zeros have opposite signs because you're just subtracting 4 if you had x plus 4 set equal to 0. See, last time there was a vertical asymptote at negative 4 and positive 4, and now it's a vertical asymptote at 4 and a hole at negative 4 because of the cancellation. So maybe you're not trusting me. Let's graph these two and see if you can tell by the graph that one's a vertical asymptote and the other's a hole. So let's do A first. X divided by, now with the division and the bottom having multiple terms, I need a parentheses. X squared minus 16. Close it. And actually I need to change the zoom. 6. Now here's the thing. On our graphing calculators, unless you're using something super special that I'm not using, this is what a vertical asymptote looks like. It kind of looks like an impulse, kind of looks like a heartbeat. It looks like it went beep, beep, like really quickly. That's because this is old technology. So on your graphing calculator, a lot of people will think that this is just the graph continuing, but unfortunately it's poorly representing the asymptote because it looks like it just continues and then all of a sudden picks up way up here or goes down forever and then picks up way over here. But again, it's going down, 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 down. It has to hop over that 4 or negative 4 and then come back from all the way up here because that's just how this one works. It could have come back from below or above. It just depends. So please understand these graphing calculators are going to make your asymptotes look a little funny. It's not going to give you those dotted lines, and it's going to misrepresent that just a little bit. So heartbeats, also known as an impulse, or what they kind of look like. And we see one of those around negative 4, and we see one of those around positive 4. Now, if I hit trace and I type negative 4, you're going to see no value for the y, which means it's undefined. And we can see, oh, well, there's that impulse. So yeah, that's happening around negative 4. If I type positive 4, same thing. No y value, which means it's undefined because there's that vertical asymptote there. So we can clearly see the vertical asymptote at negative 4 and positive 4. So hold on to that in your brain. Now let's switch the top to be x plus 4, and I'll need it in parentheses, divided by parentheses again, x squared minus 16. So remember, we saw 2 of those impulses, one at negative 4 and one at positive 4. This time we said there's a hole at negative 4, so I'm only expecting that little impulse thing to happen around 4. Let's see what happens. Look at that. I don't see that little heartbeat thing around -4 anymore. I only see it around the +4. So that is verifying that there is no vertical asymptote there. And in terms of tracing, see, look at this. If I type in -4, you might think, oh, well, that's smooth, so I should get a value. But actually, you don't, because -4 is not part of the domain, because if you plug -4 into the original thing, you actually get 0 divided by 0, which is even worse than dividing by 0. It's something known as an indeterminate form, but that doesn't matter for the context of the image itself. What this is doing that you can't see because it's so flat really quickly is it's just keeping on that way flat, but then you have a little hole, 1, 2, 3. There's an open little circle if you were graphing this by hand right there. That's what that would be. This one is going down forever, and then it's coming from up here, and then it flattens out. But around, if you type in -4.1, I got to clear my screen, unfortunately. If you type something like -4.1, you might be, oh, there's just never an answer. No, there's a value. If you type in -3.9, there's a value. The only two numbers that this thing can't handle is -4 and +4, one being an asymptote, one being a hole. And there's a big distinction. Canceled factors make holes. Everything else is a vertical asymptote. All right. C. This is going to look really familiar. Don't change color yet. F of x equals, let's go with x plus 4 over x squared plus 16. Okay. So, okay, well, let's factor and reduce this. If you try and factor x squared plus 16 with traditional factoring methods, you're going to quickly discover, I missed the S in there, discover, you're going to quickly discover that the bottom is prime in terms of real numbers. It's a sum of squares, which we said there's no traditional factor or formula for. If this was -16, it's x plus 4, x minus 4. Now, you can still set this thing equal to 0, move the 16 over, and do the plus or minus square root, and what you'd find are 4i and -4i are the zeros of the bottom. These are just arrows saying, hey, this simplifies, so I don't take up too much space. So there are imaginary zeros to the bottom, but we can't graph imaginary numbers, so it has nothing to do with the context. Now, notice I said it's prime in real numbers. What that really means is x squared plus 16, we can factor as x plus 4i times x minus 4i. Does it do us any good? No, it doesn't. But we could if we needed to, because in later math classes, much more advanced math, there are times when this does become necessary. So I'm not just teaching you some arbitrary method, I'm just trying to emphasize that this could come up later. But in terms of graphing, vertical asymptotes relate to graphing. Imaginary numbers we can't graph, so it means there are no vertical asymptotes. Because the zeros of the bottom are imaginary, there's no vertical asymptotes. Don't trust me? I hope you trust me by now. But no, the point is, you want to see this. X plus 4 divided by parentheses x squared plus 16. That's good. And this is the weirdest graph of all. It looks like it's a flat line almost. And you can see the y values are growing a little bit for a while, and then they start going back down. And it's kind of the same on the left side of the graph. 0.23, 0.2, 0.1, 0.05. This one's just going down, down, down. It eventually does actually cross that axis and then becomes -0.04, -0.05, and then starts coming back up. So this is a really weird graph, one I would not have my students graph, in fact, because of that. But you can still talk about the asymptotes. All right, let's go back to a standard Zoom window. maybe you're like, well, no, let's see what happens at 4, -4, because that x plus 4 is in the top, that could mean that -4 is a whole. But no, it has nothing to do with the fact that the x plus 4 is in the top. Wholes are found when you see that in the top and bottom. So it's a trace, -4, and look at this, we get a y value. It's at exactly 0, in fact. What about +4? 0.25. So there are no wholes, there are no asymptotes of C. That's it, that's all there is. So that's our vertical asymptotes. That's one of the two things I'll be testing on from this section. The other thing being, this is just the same work again. Oh boy. I'm gonna regret moving that, aren't I? Oh, crud. Okay. That's all right. This is just gonna take me a minute. Just start writing where it says horizontal asymptotes as you see it. Word is really fun. It's so weird how the text and the handwriting stuff interact or don't interact. Horizontal asymptotes, the other ones. So vertical asymptotes are found by setting the bottom equal to 0 after reducing. Horizontal asymptotes completely different. Horizontal asymptotes are based on the degree of the numerator and the denominator, and that's it. Degree meaning just the largest term. So we're only looking at the largest term of the top and bottom, and by largest I mean the term with the biggest exponent. So you find the term with the biggest exponent at the top, you find the term with the biggest exponent at the bottom, and that's it. If you've got 5 or 6 or 17 terms in the top, ignore them all but the biggest one. Same thing in the bottom. So these horizontal asymptotes occur as x goes to plus or minus infinity. That's what that's saying, as you go right forever or as you go left forever. That's what this as x blah, blah, blah means. Here's the idea behind a horizontal asymptote. We've talked about how the leading term of polynomials takes over as you go into the hundreds and millions and billions. So that's why we talk about the end behavior just based on the leading term. Horizontal asymptotes are the end behavior of rationals. So what we do is we just think about the end behavior of the top versus the bottom. So all we do is just pretend like the leading terms in the top and bottom are the only ones we have. And as x gets really, really big or really, really small, that thing takes over and you just reduce it. And whatever that thing looks like is what you'd look like at the ends. So the basic idea is you'll either look like this, an x, which means you're going up and down forever, so there is no horizontal asymptote, or you'll look like a constant, which is the third case, so I don't want to say that yet. Let's do this in order. The first case, if the degree in the top is larger, that means if you just took the leading terms and reduced them, it would be like x or x squared or x to the third, whatever, which means they go up and down forever. If the degree on the bottom is larger, that means you're looking at something like 1 over x, which we just graphed, and we said that they go just flatten out. They flatten out to a height of 0 specifically. So that's the second case. If the degree in the bottom is larger, basically your function looks like this, which means the horizontal asymptote is y equals 0. You're just flattening out to that axis. The third case, if the degrees are equal, what you end up getting is something like if you had 7x squared in the top and 2x squared in the bottom, you'd get 7 halves, just a fraction with no x's. It doesn't have to be a fraction, could be a whole number. And then that number is the y asymptote. The horizontal asymptote. I don't know why I said that. I was looking at a y. That number would be the horizontal asymptote, which is literally just a ratio of the leading coefficients. So I've explained this 2 ways already. We have straight up memorization, which is the bullet points. Or we have considering what the functions would look like if you reduce them. Now, granted, this way is more of a calculus approach, but I imagine half of you are going on to some form of calculus. The reason you're in a pre-calculus is because you're going to go to calculus later. You don't get a pre-job and then not a job, which school I feel like is probably the pre-job. So we're not going to have time to do any examples. I will, you can kind of see the first one peeking at you, but I'll explain it next time. So let's just take the last 1 or 2 minutes. You can write that down. We'll come in guns blazing at these horizontal asymptotes next time. That'll finish this section. Then we'll finish 3.7 probably in like 40 minutes as well, because it's a pretty short section.
All right, so with that being said, we'll close out the day. Your due dates are up on the board. Obviously, the 3.2 one has passed. We don't need to see that anymore. Not that it matters. 3.3 is the 15th. 3.4, which we finished at the very, very, very beginning of this class. We're going to have that due on the 22nd. And then, like we said, we'll talk about 3.5 next time. By the class after that, we should finish 3.7. Actually, no, we'll finish 3.7 next time as well. Sorry, I'm getting my days mixed up. So on the 20th, we should finish up chapter 3. As I've said, we're going to do an abridged version of 3.5, and 3.7 is pretty short. So with that being said, that puts our test 1 week after that. Now this test is going to work just like the last two. There will be a review in my math lab, which I'm going to go ahead and make active today, right after class. So in a couple of minutes, it's what, 9:13 right now. So in a couple of minutes, I'll activate that so you can find that in the same place as the first two reviews. And then the test itself will be very similar. The main difference with test 3 is that you are now allowed calculators, as we talked about class. They are great tools, no longer just crutches. But you are still responsible for showing your work. You still have to upload it to Canvas within 15 minutes. We'll have that link ready on the appropriate days. And the final exam won't be too far around the corner after that, but I don't want to talk about too much all at once and overwhelm you. So we'll get to those details sooner than later. But for now, have a good one. Have a good weekend. We will see you on the 20th, ready to close out chapter 3. Take care, everybody, and email me if you have any questions.